Welcome to Unsupervised Thinking, a podcast about neuroscience, artificial intelligence, and science more broadly. We're a group of PhD students studying computational neuroscience. I'm Grace.
I'm Josh.
And I'm Connor.
And the topic for this episode is deep learning. And today we also have a special guest. Connor, do you want to introduce Ryan?
Yeah, so today Ryan Tombacco, a good friend of mine from Ireland, is going to be joining us. He is in Galway right now. Is that right, Ryan?
That's right.
Cool. So yeah, Ryan and I did undergrad together, and he's a glorious human being who is basically a non-expert, but kind of, I think, probably pretty interested in this topic. So you're kind of representative of our target audience, I think, and you will hopefully ask us lots of questions and just chat with us about this topic. We are theoretically somewhat informed. I guess Josh and Grace can kind of call themselves, proper researchers in this field at this point. Let's just kind of talk about it and learn. Hopefully you'll learn and we'll say things.
Oh. So deep learning is a pretty big topic, so we'll just go through some kind of overview of all the different areas it touches and a little bit of the background and everything.
Maybe to start out, we could ask Ryan what he's heard about deep learning, like through the media, or whatnot, and what interests him about the topic.
Sure. I'll tell you, you hear the term a lot, but I don't know if you hear the definition of the term, just how the media likes to portray that it's being done and they have cool experiments. So I'd say that my layman's understanding right now is that we have general learning in place for a long time with computers, algorithms, and so on. It's not particularly clever. It's very mechanistic. And then deep learning is some kind of abstracted level of that, where the machine can not just, go from supervised to unsupervised or something like that, but can teach us something from the learning. Does that make any sense?
Yeah, no, I think that, that's a great starting point, and I think that's kind of, maybe what someone, coming to this, having read things in popular media, might be expected to know, or the opinions they would hold about it. So maybe we should start off by kind of just giving sort of some sort of concrete definitions or framing of the problem.
Yeah. So it's considered a part of machine learning and also a part of the field of artificial intelligence. Generally, these algorithms also fall under the category of artificial neural networks. And so this all starts kind of with the start of the study of artificial neural networks back in the 60s is when that first started. So we can give some of the detail of that. So the original notion of an artificial neuron, it was called a perceptron. And basically what it is that it's kind of considered like the artificial neuron is considered a node or a unit, and that node or unit gets inputs, and those inputs each have their own weighting, and then you kind of multiply an input by its weight, and then you sum it up, and then you get a number, and basically if that number is positive, it means you have one category, and if it's negative, it means your input comes from a different category, is a way that these things are applied. And so that's kind of the basic unit of artificial neural networks, and when you put a lot of those units together and add other complications to them, you can create a large artificial neural network that can do somewhat complicated computations and give you interesting outputs as opposed to just this yes-no output that you would get with a single perceptron. And
kind of originally, when it was kind of first posed, it was kind of dovetailing off of thinking about it as kind of logical decision making. So classification, which is now kind of a big problem that's been solved with deep learning, was kind of, it was originally kind of the networks were thought to be like doing logic, making decisions about which of two categories something fell in with this threshold. And you could add more categories and more complexity by, as Grace said, combining lots of these units together or kind of stacking many layers of computation.
Yeah, and what's interesting is that this whole adding complications and stacking, that's very non-trivial. And in fact, after these perceptrons were first developed, it was kind of discovered, so to say, that that just the single perceptron, as I initially described it, could only do very simple classification problems. They're called linearly separable problems, and most interesting problems in the world do not fall into that category. And so there's kind of what's known as the AI winter, where people stopped studying these things because they thought that they could only do the simplest of classifications, but all it really took is adding a few more layers of these and adding a few more complications to get them to do far more interesting things.
And essentially, contemporary deep learning really does follow this trajectory, though there have been kind of, these pauses and people picking it back up again. And the kind of recent stuff has been, how do you train successfully recent, past 20, 25 years, and, with incremental improvements since then, how do you train these big neural networks with lots of layers and many of these units? And kind of what kind of bells and whistles should go into this to make it work for big problems.
Yeah, and to be clear, when we say train, as I said, this initial perceptron had inputs, and then there was weightings on those inputs. And basically, when you're training, you're trying to figure out what those weights should be. Because you're already given the inputs, you know what those are, and you know what you want the classification for each set of inputs to be. And the question is, how do you weight those inputs to give you the desired output?
So I feel like we've jumped really far ahead really quickly, and there's tons of terms that we should probably kind of just briefly define and stuff. What do you think about that, Ryan?
Yeah, let's get some more info. Sounds good.
Okay, so machine learning and artificial intelligence, what roughly are those things supposed to be? We haven't really ever explicitly stated what machine learning is.
I mean, I think that there are sort of different ways of looking at some of these fields. I mean, artificial intelligence was kind of the study, largely originally by computer scientists, of the ways that artificial systems can do things that seem intelligent. And machine learning is kind of a recent, statistically more rigorous reincarnation of similar fields that kind of combines approaches from computer science and statistics and sort of tries to formalize relatively straightforward and easy problems like classification, picking which of multiple classes something like an image falls into.
So let's give some. We were talking to someone in a bar the other day, and we gave just really simple, concrete examples, right? Because people hear about machine learning in the media now. I guess part of the reason for that is because machine learning techniques in general, not just deep neural networks, right? So deep neural networks are one type of machine learning or artificial intelligence algorithm model. But machine learning in general is used for a lot of things nowadays. For example, when you use Netflix, there's a recommendation system. So based on what you've watched previously and what all other users of Netflix watch and maybe other kinds of information, there will be machine learning algorithms which take the data and in some sense learn from it how to kind of recommend to a user what he or she should watch next based on what they've already watched. Or Google Translate uses machine learning techniques to basically improve, to learn from big databases of language. I guess they probably use already translated text, text
in many cases,
humans,
they have
things like this.
Text where there's multiple corpuses.
Yeah.
So kind of a specific company's algorithm is going to be kind of under the hood. It'll be a mixture of things, and it might change over time. And it's kind of the products what they present forth. So Google Translate uses various machine learning techniques to do translation from one language to another.
Object recognition is a big thing. So there are now algorithms where you can take an image and you show the image, you pass the image through some algorithm, some machine learning algorithm, and that algorithm can kind of attempt to tell you what objects are present.
Maybe even write a coherent caption for that image.
Yeah,
and some of these things have definitely been enabled by deep learning techniques. So before deep learning, there were other techniques that people used to try to solve many of these problems. And in some of these cases, the first techniques which have really done a good job, like a job that a human would evaluate and say, yeah, this is adequate performance on this task, like captioning, have been done basically by deep networks which were trained specifically on that task. And when we say trained, so there's a lot of kinds of deep nets that people have worked on over the years, but much of the current enthusiasm is for supervised methods, which essentially means you start with both sides of the problem. You start with some labeled data where you have an input and the desired output. You have a big data set of that, and you train your model such that it can do that for other data points. So you start with many, many labeled images where the label is the caption for the image.
Someone had to label it, right?
Humans have labeled that. It's available on the internet if you're a place like
literally someone looked at an image and said, oh, there's a banana in this image, and they wrote banana. So now there's a data set that consists of that image and the word banana and many other images and words describing what's in them.
Yeah. And then, at the end of the day, you train your model using some set of techniques to do this. And then once the model's trained, you can evaluate it on other images. So put an image in that's a different image of a banana that the model's never seen. It'll be able to tell you it's a banana, or it might be able to do something more sophisticated like generate a caption for it or something like this.
And the reason that it's called learning, again, is because it does require that you have all this data that you show to your algorithm. Your algorithm changes in some way, and then it learns to do this sort of thing. You could imagine just generically an algorithm is just written by hand, and it just takes inputs and spits out outputs, and nothing about the algorithm changes in that process. It's not learning in response to data. But the big breakthrough has been this notion that you can have these algorithms learn over time based on the inputs that they're given.
So, Ryan, maybe you can ask questions, anything that you don't understand.
Well, I did have a question based on what you guys were saying. We've gone over the previous types of learning. I say previous; they're still happening, I guess, but deep learning has obviously get a lot of traction. Is it synonymous with using neural networks?
There are many kinds of neural networks, and some of them are more or less biologically plausible. But currently, when people talk about deep learning, essentially all of deep learning takes the form of a certain kind of artificial neural network. A certain kind that in general isn't super biologically plausible in that it's extremely simple models of neurons that they just kind of instantaneously add their inputs and give you an output. It bears resemblance to real neurons, but it's certainly a dramatic abstraction.
So yeah, it's not synonymous, but...
Well, so there exist neural networks that people study in science that have nothing to do with deep learning and aren't really used for sort of engineering applications. But all of contemporary deep learning does use neural networks.
Yeah. And when people say artificial neural networks, pretty much anytime someone says artificial neural networks, they're talking about the kind of neural networks that are used in deep learning.
Yeah, that's a kind of weirdness of the language, that artificial neural network, that exact term usually refers to the kind of computer science engineering side of things, whereas people who do computational neuroscience also create artificial neural networks in their computers, but they just call them circuit models or something like
Spiking
that.
Neural network.
Yeah. Or maybe biologically plausible neural network models or something.
Like that.
Yeah.
Okay, that makes a lot of sense to me. So we know that a subset of neural networks are used in deep learning here. What makes these neural networks, good for deep? What are we getting from them that we don't get from just the use of neural networks as a whole?
Well, so there's a few things. For the purposes of doing artificial intelligence, obviously you need things to be as quick as possible and as easy to work with as possible. And so that kind of speaks to why these artificial neural networks are so much simpler than the biologically realistic ones that some other scientists are interested in, just for kind of ease of study and use. Also, these networks that can perform these tasks are not constrained to the biology, so they can use tricks that don't relate to biology. But really, the reason that these things have taken off lately is just because we've had the computational power to make really big artificial neural networks, and we've had the data to train them on. So
up until very recently, it's not like you would have had 100,000 labeled images from 10 categories or something like this. And now, that's not categorically true. For a long time, there was a data set called MNIST, which is kind of an early data set that's been used for a long time, which was essentially a character recognition data set for digits. So it was the digits 0 through 9, and there were, roughly 10,000 or so.
They're handwritten digits from
characters,
the U.S. Postal Service.
Yeah.
So you want something to be able to read postcodes automatically, I think.
Yeah, and this was solved, a while ago at this
late
point.
80s when Jan LeCun first came up with a good way of doing that.
So the data set is essentially a whole bunch of digits, handwritten, so there's lots of variability for each digit, and you have many copies of them, and you want to train it so that at the end of the day, the model can take in a digit that's represented as a, like roughly 32 by 32 pixel square that corresponds to the black and white image of that character, the handwritten character, and process it and tell you what digit that is. That's basically the problem. It's like a very tightly constrained problem.
Yeah. And so as soon as people started having these kinds of data sets available, it obviously made it possible to potentially train these neural networks on those data sets. And then when computers became more powerful, it could really all be scaled up a lot.
So while you could do a 32 by 32 image a while ago, only recently have you been able to successfully perform this on like a 500 by 500 image, or on like an audio track where we could do like, speech to text kind of.
And not just the actual size of the image, but also kind of the complexity of what you're categorizing. So instead of just saying, is this 0 through 9, you could say, what kind of dog is this? Or is there a dog here at all? Or things that are kind of far more complicated to recognize out in the real world. Because you could make these networks that perform it even larger and more complicated, and they could capture more complicated structure in the categories that they're interested in.
So something that I think a lot of people might get confused by, let's say, with learning, is that when we're not talking in this world of artificial intelligence, learning is used in many different ways. I can learn a language, I can learn all kinds of things. And the kind of learning that you guys are talking about seems to be very specific problem-solving learning. Now, would you say that something as complex as learning a language, I can imagine identifying a picture is pretty complex. Would you say that those are all just higher level problems that we can start to approach with deep learning? Or are they very different categories of problems that we need to break them down into sub-problems?
That's a cool question.
Yeah, I don't know what we need to do. I know kind of what people do for different types of problems in this community. And so usually what it corresponds to is using different architectures for the network that you're training.
What do you mean by architectures?
You have all of these individual nodes or units in your network, and you can come up with different ways of connecting them. And that can include maybe you just have, 2 layers, and there's 100 artificial neurons in each layer, and you just let them all be connected to each other from the first layer to the second layer. And then you just try to figure out the weights. Or you could
So learning in that case is learning those weights that you've specifically specified what those weights correspond to in your model.
Does that make sense?
I think it does. I don't want to interrupt Grace there, but when we're talking about learning the specific weights, there's, in my mind, tell me where I've misunderstood, learning a weight is knowing what a neuron is going to do under a situation, but knowing what that weight corresponds to in real life is not necessarily known, right? Oh, let me try and give you an example. Let's go back to Netflix. It's my understanding that in other styles of learning, once you've been able to learn something, you can actually identify, hey, when you like this genre with this actor, that's very likely. With neural networks, can we break out what weights actually correspond to what we need to prioritize in real life learning?
To some extent, yes, but it's sometimes more subtle. So depending on... So this is kind of more just a general problem. In machine learning and statistics, one way of thinking about what the people do is they specify a model that seems appropriate to the problem. And then they use some technique or algorithm to find the values of the free parameters in that model that they've posed, which they pick that model, or in this, like in deep learning, like the architecture is the model. They've specified that model because they think it's right for the problem, but they don't know the exact values of the various parameters. So you use some technique to find the values of the parameters. And in some models, those parameters are easily interpretable, and in other models, those parameters are not very easily interpretable. So like linear regression, which I won't get into for people who don't know of it. For people who do, it's probably a very straightforward thing. Takes some features and produces a prediction based on those features. The inputs to the linear regression model are those features. And if, there's basically one parameter per feature. So you basically can say what's the strength or relevance of given inputs to your model just by like the value of the weight that corresponds to the thing. But in a more complicated model, sometimes that kind of intuitive understanding of what the parameters correspond to in the model is there for the scientist or statistician or engineer or whatever who's building and working with the model. And other times that intuitive understanding is kind of obscured because there's so many parameters, or the parameters are interacting in very complicated ways. And in deep learning, it's kind of the case that in some situations the parameters can be obscure, and there have actually been people who have written papers about how to interpret what deep learning models are doing. So kind of people can get a sense of what deep learning models are doing, but granted they are kind of more complicated models than other settings.
Yeah, it has a very black box flavor a lot of the time, right? You use basically, what is a deep network? I guess we haven't really even specified that. It's all these units, but typically when someone says a deep neural network, it also has this kind of feed-forward architecture. So you have neurons in layers, and what a layer means is that if I'm a neuron in layer 2, a fake neuron, I receive input only from neurons in layer 1, one layer below me. And then neurons in layer 1 receive input from the world, like they receive the raw input, say. And then you go
like the pixel values of your image.
The pixel values of your image, for example. And you go up through the layers, and there's a top layer. And then often people will kind of put on top of the top layer some classifier. But anyway, what you end up with is kind of this big model that has lots of free parameters, the weights being the free parameters, plus maybe free parameters of the classifier that sits on the top. And all of those are just trained with gradient descent on some cost function.
Which we'll get into what that means more specifically in a little bit. But yeah, so just to go back to this idea of architectures, as Connor was saying, you have all of these layers of neurons, and you can make decisions about how many neurons are in each layer. You can make decisions about if you want, maybe you want the first neuron in layer 2 to only get input from the first 3 neurons in layer 1. You can write that in as a constraint before you even try to train anything, if you think there's some reason for that to make sense for the data that you're working with.
Or possibly just because if you add more constraints to the model, you need less data to train it.
Yeah, there's fewer parameters. If neuron 1 in layer 2 is only getting 3 inputs, that's only 3 weights you have to learn rather than the entirety of the first layer onto the first neuron. So there are decisions people make about the architecture, either for ease of training or because they believe that those decisions are relevant to the type of data that they're looking at. And an example of that is when you're doing this kind of processing of images. Basically, there's the style of network that is most commonly used for that is called a convolutional neural network. And just simply what that means is that rather than just having all of the input pixels just be able to connect to all of the units in the next layer, you kind of have a little pattern that you scan across the image, and you kind of see how similar a little chunk of the image is to that pattern at each location. And the reason that this makes sense for images is that, you might take a picture of a cat, and sometimes the cat's face is right in the center of the image, but sometimes it's a little off or a little up or something, and you don't really want those small differences to impact the fact that you call that a cat. So you just want to kind of look for certain features all across the image, and then you can be invariant to certain spatial translations of things. So that's an example of using your knowledge about the input to decide how you're going to connect the neurons in your model.
So this all stemmed off of your question about more complex learning, right? Learning things like learning a language and whether or not they can...
In fairness, I got more complex learning out of that question.
Okay, cool.
So then for something like learning or for producing language, that's a whole different type of model, and that will use different types of units that are connected in a different way. A lot of times that goes into a different class of artificial neural networks called recurrent neural networks, which means that rather than have this clear layer structure where layer 2 only gets inputs from layer 1, you can have cells that are technically all in the same layer that connect to each other. And that gets a lot more complicated because then it's not so clear how one neuron affects another, because it can connect to it directly or it can connect to another neuron that connects to it. And so those are a different style of network, and they're a little bit more complicated to train.
So like the idea there would be, I mean, roughly is that somehow this recurrence gives you some kind of memory and makes the model maybe more naturally able to operate on kind of sequences of data,
because
language being, sequential.
Yeah, there are certain probabilities. If you say, the word you, it's probably going to be followed by a verb or something like that. And there's dependencies that last over time in language. And if you have this neural network model that can connect to itself in this interesting way, it might be able to capture those dependencies over time.
The dependencies in the language. And so traditionally people have called this a language model, and there exists kind of whole repertoire of standard techniques that people in machine learning and engineering have been doing to try to process language using statistical models. This field is called natural language processing for a while. And in deep learning, you can use the kind of techniques that seem suitable or appropriate to deep learning to solve these similar problems, like modeling language this way.
But it's an interesting question. Like what, the full problem of learning a language versus the fanciest machine learning language processing. I don't know. You guys probably know. What's something kind of cool that they can do now in natural language processing?
I mean, I think generating captions for images.
Yeah, and that actually.
Compelling.
So, Ryan, you were asking if it's kind of broken down or something like that. And I think the captioning and also translation, machine translation, are examples where they do break things down into separate types of networks for different jobs. So with this image captioning system, they do what I described earlier, the convolutional neural network for images. They kind of put an image through that, and then they get some representation of that image that they can then put into a language generation model. So you have these two different types of neural networks that we just talked about that kind of come together at a point so that you can have language generated based off of an image as an input.
So this leads to so my next question on that, seeing as we're talking about language, what you seem to have said is that if we break it down as we have done for captions into sub-problems, I have one neural network of one architecture solving sub-problem A. It reads to an output, which is the input for neural network B solving problem B, right? Does the brain work like that the neural networks can be separated? Can you just do one solid output into one solid input? And, is that just a limitation of how we use computers and what we can do right now?
Well, so just to be clear, you can sort of train these subnetworks for these problems separately, or you can train them all together at once by just, you could basically specify it as one big network that's like the composition of two smaller networks, and then you could train it all together. But so there isn't necessarily in all cases a clear separation between the two subnetworks, but the people when they're building the networks might think of them as separate. And in some cases, you might train them separately first and then train them more together. Or if you had enough data, you could just train them maybe all at once, possibly. We don't know how the brain works, but I mean, to some extent, different brain regions do different things. So it's reasonable to think maybe that different brain regions are specialized either genetically or through learning, or some combination thereof, to handle sort of sensory specific things, right? So like visual cortex is the part of the brain, the cortex, that receives input from the retina, and so the visual world basically. And as a consequence, the way it's going to process stuff is going to be mostly vision first, right? And then a different part of the brain, auditory cortex, receives information from your ear, and so that's going to process auditory information in a way potentially that's specialized to auditory information. And then another brain region will receive inputs from both of those brain regions, and possibly form some sort of multimodal representation, where multimodal just means it's combining a couple different senses in this case.
Yeah, I think as a rough approximation, it's a reasonable thing to kind of assume that you have this one pathway that processes visual information, and then the condensed representation of that visual input is kind of passed on to other brain areas. Because, if you damage part of the visual pathway in the brain, you don't really damage people's ability to speak. You can kind of have separate, localized functions in different areas and that sort of thing. So roughly, it's similar. Maybe we should kind of discuss a little bit more detail about how these things are trained?
So there's one thing I wanted to cycle back to. Ryan, earlier you asked, what makes these kind of networks different, or why are they kind of different from previous machine learning methods? And we danced around this, and your kind of original intuition about deep learning that you'd garnered from what you'd read kind of suggested maybe deep learning tells us something more interesting or specific or better about the problem that it is focused on, and or is better than conventional machine learning methods. And so different people have different opinions on this. So I've heard people criticize most of machine learning as kind of being glorified forms of regression. So the idea is that conventional machine learning, and this is not categorically true in my opinion, but conventional machine learning is largely, if you solve a classification task, and certainly in industry this might be more true than in academia, but conventional machine learning, to solve a classification task, you just use something super simple where you throw all of the information you have about the problem into a big bag and do some simple form of a classifier. Something very simple that's kind of out of the box and built into most packages that people would use to do this kind of analysis. So one cartoon of machine learning is that that's what it is. And the thing that you could say then about deep learning that's different, and kind of another title for deep learning, is representation learning. So instead of just taking your whatever information you have about the problem and throwing it in a bag and performing something like regression, deep learning, through learning of weights, is actually kind of learning the features of the problem that are relevant. So in the case of having an image, previously when people tried to do image classification, they would hand engineer features. And by features, we just mean something that they looked for in the image automatically. And then they would do something like regression based on those features that they hand engineered.
And so they would kind of think about, what's informative in an image? Maybe if I know something about the number of edges in this image, or the spatial frequency of this image, maybe that's informative. And so they would build these features that are based in just mathematical formula that they could apply to the input image, just to get some measure of some other kind of more higher order structure that they could find in the image, and then just use that. So they had to just kind of think it through based on the domain that they were interested in, if it was images or audio or something. They just kind of thought about what might be important, and now we kind of take the thinking out of it.
Deep learning kind of lets you make that more automatic. If you can devise the right architecture for the problem and train your deep learning model, then the feature engineering is eliminated, and you can even visualize the features of the data that the algorithm learns to care about in order to solve the problem.
Does that make sense? You've asked me about that before.
Yeah, it definitely makes sense. I'm more. I'm not going to say it conflicts. It doesn't match a little bit some other stuff I heard about features. So you can clean up what my knowledge is there. As my understanding was that when you use other learning algorithms, some of them tend to be heavily feature-based in that the user has to supply the features, like you guys were saying. So we work out how many edges something has, how many changes from dark to light, whether there's circles, whatever it is. And with neural networks, the weights are kind of approaching that on their own. So you don't give them the features, they're extracting those features, and they're extracting the right features. Now, it sounds to me like priming the nodes is similar to trying to tell them what the features are. So it sounds like it's more halfway. We aren't saying we'll give you all the data and you just do whatever you want. We can actually say we'll give you the data and we'll also give you some clues while we're at it.
You mean setting the architecture gives clues?
Yes.
Yeah, you can look at it a little bit that way. It still is the case that even if you say, okay, this node will only get input from this section of the image or something, it still is the case that these networks kind of find on their own what we now kind of consider the right solution, which is looking at kind of, these oriented line type filters to find edges in the image. But that actual solution of finding an oriented line isn't really given by the humans when they determine the architecture in any very explicit way.
But I mean, clearly,
that's true.
Yeah, there's clearly a relationship between finding the right answer and setting the architecture.
Yeah.
And the better you set the architecture, the more likely that less data will successfully find a good answer.
Yeah,
that's basically a way of thinking
the
about
fewer parameters you are, roughly in some way, the less data you need to get a decent model specification, i.e. a set of parameter values that work fairly well. But like in theory, you could just take whatever your little model of your artificial neuron is, you could just take that, you could say, let's have 5 billion of them, let's let every neuron be potentially connected to every other neuron, and let's just train all of those weights. And all of the architectures that we've kind of mentioned could theoretically be learned out of that process.
Yeah, so and one way of thinking about that maybe is like, that's like a thought experiment from one extreme of how the brain could hypothetically work that we believe it doesn't work, right? Is that like you're born with a mass of undifferentiated neurons that are all totally identical and connected to every other neuron in your brain. And it's exclusively through experience that your brain comes to take the highly structured form that it has. Now, we know this to be false, right? Your brain is already relatively highly structured by the time...
You can consider the choosing of an architecture in a deep network akin to genetics, in that it lays out a rough plan of how things should go. And then you learn the details.
You clearly have to learn some stuff from life, and that's what actually, kind of prunes and tunes how your neurons work. We're making this as a hand-wavy, kind of speculative, though broadly plausible comparison with the brain, right? Not to be taken exactly literally. Make sense, Ryan? Any more thoughts? Yeah.
It definitely makes sense. This idea that the brain is primed by genetics and so on, I'm going to, like, in large cases, obviously, we're talking about by evolution over time. I mean, I'm sure that there's some things can be passed, from parents to children or whatever, but at the neural level, I'm assuming that isn't as big a player as thousands upon hundreds of thousands of years of priming the brain to be what it is.
Well, so, this gets to me like an interesting, divide in philosophy that people talk about, which is the distinction between like innate abilities versus how much is learned. And, depending on which kind of circles you talk about, people would, trace this back to Plato and Aristotle. And there are other kind of thinkers that fall on various sides of this. Like people associate Kant with the Platonic side of this, which is like that much of the way you perceive the world is innately determined by, like, let's say the structure of your brain, if we're sort of generous and retrospectively reinterpreting the way that they would have thought about this. So something about your soul or the nature of humanity, kind of the way we think about it now, your brain is what determines how you perceive the world. Versus like a notion of it kind of being totally learned, which, by some hand-wavy connection relates to the way Aristotle more looked at the world, that, you look at the data and, kind of the strong empiricists in philosophy would fall on this side of it. That's kind of much of your learning of the world or much of the way you learn to perceive the world is totally shaped by just your experience of it. And so, we're touching on this, I think, the notion of architecture as kind of the middle ground here, where it's the architecture that's kind of innate, maybe, and the data kind of constrains or the data determines what that architecture's, parameters become. That's kind of a reasonable middle ground between these otherwise extreme views.
Well, the interesting thing then, between those two ideals, so the idea of what are you born with is innate, can you do, and what do you learn over time, and obviously they interplay. With current deep learning models, what directions are we seeing these take? Are people trying to improve the functionality of the model, improve computational power, harness, more data to throw at it, and think we're going to get all of our solutions by doing this? Or people going, no, we need to understand architecture better, we need to understand how this is primed and prime it the right way for the result? Is the reality going to be in between?
I think, that's like a great sociology of the field kind of question. And I think a lot of it depends on what biases people bring to it based on what other problems they've worked at. So, like, if you're...
Well, Josh, tell me what the right people think.
I think if you're, a researcher in industry where acquiring large data sets might be cheap, maybe your bias maybe someone at a Google. I mean, not everyone. I don't. There's a lot of people who work on this at Google, but maybe some of the people at Google might say, yeah, we can use simple models and throw lots of data at it. I've heard this stated by someone who works at Google. We can use lots of data, like simple models, and throw lots of data at it, and we'll solve the problem well. Whereas other people, there's definitely a camp, maybe from conventional machine learning and statistics that would be inclined to try to initialize the parameters very well, because these problems don't guarantee you get to the same solution depending on where you initialize from. So there's going to be a camp that's going to fuss about what initialization to use, expecting that can change the performance a lot, and perhaps it can. Other people will tweak the learning algorithm a lot. That's probably most common in the deep learning world. Is just
change how you learn.
Change how you learn. Yeah. So change the rules by which you update the parameters.
Yeah. And then, there's a slightly different divide between people who tend to be in industry who care most about just getting it to work well, and that might mean more data or fiddling with the architecture or the learning method or anything that they hear will make it work better. If you're at a company and you need to get something done, you just want to know what will work best. And then there's the more academic types who occasionally are also interested in neuroscience and consciousness even, and all kinds of things, who tend to ask more the questions of the architecture and what does it mean and how does it work, not just does it work. So there's a divide in that direction as well.
So some things that come to mind just as an example of, I guess, playing with architectures, when it comes to recurrent neural networks, in that domain there are a bunch of kind of specific things like LSTMs, long short-term memory, just like a specific little architectural piece.
It's basically what the node that you're using.
Yeah, the people kind of come up with to attempt to solve some specific problem, and in that case it's kind of having some explicitly more long-term memory, or like there's a thing called like a neural Turing machine, which is a similar idea, kind of explicitly building into the architecture in some way mechanisms that we look at, the people designing them look at and think, oh yeah, this is a mechanism, a direct mechanism for like having longer term memory or something, and I think that's going to be useful for whatever kind of problem. So there's those kinds of things, like all of these things happen.
And with this architecture, do we tend to I'm thinking more of the physical sciences here. I have a theory, let's do I have a hypothesis, I think that this kind of architecture could lead to that, let's find out. Or is some of it actually coming from, so we ran this, it ended up in this architecture, that's pretty cool, I learned something new I can use in future models?
I think it's a lot of tinkering. It's a lot of grad students trying different things, and when it helps, they publish it.
Yeah, and by help, so the kind of thing you need to do to say you've done something in this field is usually solve a problem better than competing algorithms are currently solving it. And by competing algorithms, we mean any part of it. The learning rule or the architecture or something. Basically just build some, kind of incremental improvement on an existing approach. Usually it's incremental, though sometimes people will try a totally distinct approach. By totally distinct, we don't mean like totally distinct, right? We mean like still kind of within the realm of what other people were doing, but yeah, different flavor. And often with lots of creativity, right? I don't mean to make it sound like this is trivial. Like a lot of these ideas are really creative. And yeah, you compare against the performance of other algorithms on some like benchmark task.
Yeah, there's a lot of standard data sets, depending on the type of problem you're working on, that you can test your algorithm on, or your tweak to an algorithm on, or whatever it is that you're tweaking, to see how you compare to other people who are working on the same problem. And that's usually published in your paper, is your performance compared to the most recent best performers.
And what I'm sure is always the usual layman question of, let's use what we know to get what we know. Can we use neural networks to teach neural networks to learn from other neural networks?
So there's actually been talk about this kind of idea. At some point, something like this was called dark knowledge. I'm not an expert on this, but yeah.
Was the name of the researcher involved called Lord Voldemort? Or?
No, but someone quite famous in the field. I believe Jeff Hinton coined that term. He's like kind of the grandfather of this whole field.
we talked about the comparison of having architecture versus throwing data at something and the kind of benefits you can get from that and what people think. So what about quantity over quality, like we're saying here? The idea of, do we just throw in more nodes and hope something finds something, or do we make it leaner, more efficient for the task? I guess an analogy to that question would be, if I want to be a better learner, do I make my brain bigger, or do I tinker with my brain so it performs better?
I like that analogy. I mean, I think people conventionally in deep learning, so these models take a very long time to train. I mean, we're talking like, often when people are training things for state-of-the-art performance, certainly takes like hours on the computer, sometimes weeks on the computer, or possibly longer than that in some cases, but probably, there's like a nice paradox that's come up in other fields too, where like if you started training something on a contemporary architecture that took 6 months to train, probably people would have developed like better computers and better algorithms by the time you finished training it, so you were wasting your time. This kind of thing comes up in space travel too. People talk about, but
deep learning is like space travel.
Deep learning is like space travel.
But they make less action movies about it, unfortunately.
Someday they will.
But I don't remember what the question was anymore.
Should I make my brain better, or should I make it more efficient?
I think, that's very intimately related with how much data you have. Because if you have more nodes, you have more parameters, and so you need more data to be able to train that. So maybe you could ultimately get to a better solution if you had the proper data. But if you don't have quite enough data, then put more effort into having fewer connections, but the right connections, I guess, would be the knowledge of the field. Right?
Also, like how, for a given increase in performance, how much more data you need per extra parameter or something, like what the shape of that curve is.
Yeah, so I don't know if people always have bothered to characterize these, but in many cases people just practically make the biggest architecture they can train.
Yeah.
That was kind of what I was going to say. So just the practical solution is see how big you can train something given the amount of time you're willing to expend.
And people have sort of, I guess, quantified this, right? Like take some task, take some architecture, increase the number of parameters, and see how performance improves.
Yeah, usually when people publish their results, then they might publish a few variants of the network that they used by changing how many nodes are in each layer or something like that, just to show the kind of span of performance that's possible with their architecture.
Similar family of models. Yeah.
It makes sense. I see what you're saying, especially the efficiency question of how efficient is it to go quantity over quality and vice versa. But at the end, what we're trying to get, like you guys have used the word a lot. I was surprised, maybe it's the right way of saying it, but the word right. How did we learn it right? Did we get it correct? And in my head, a lot of learning, is there even a right answer? Sometimes learning is about things that are more, let's say, subjective than objective anyway. Like, in a banana in a picture, that seems right for most bananas, but there's some outlier bananas that you wouldn't know about. Right?
No, this is a great point, but this is all philosophically swept under the rug and should be in these settings, right? When you decide what you're training the model to do, you specify what right means, right? If you've given it a set of labeled data where the bananas are all labeled, if in my labeled data I give a picture of something that's like a dog eating a banana or something, or a monkey eating a banana is maybe more plausible, then, and if we label that as a banana, even though it could have equally been labeled as a dog.
That's just a decision you make when you're labeling your data, and then you just stick with it.
It makes sense for classification. What about other problems? Let's say Netflix recommendations. How do we define what's right about what recommendation is the right one for a particular person?
Just like that one, I don't know if they're using deep nets for. I mean, perhaps they've tried it. The solutions that, like, for a while, this was a very popular problem, and people weren't really using deep learning as much as other methods, as far as I know. But yeah, I mean, I think in those cases, in order to train a model using supervised methods, you kind of have to know what it means to be right, and you specify that, and that's something you fiddle around with until you subjectively assess the model as producing reasonable outputs. So a lot of this, is just kind of swept under the rug. There are other models that, kind of using certain kinds of unsupervised techniques and things like this will give you new ways of looking at your data, and then you can kind of make decisions about it. But yeah, I don't have a good generic answer for that.
But So I was going to say there's a subtlety as well when you talk about kind of the right solution. So there's the performance on the metric that you've defined, which is the label of the image or whatever. And then there's the solution in terms of the whole set of weights that the network discovers. And for that, we can't pretend that there is some single right solution for what all the weights should be, and we're just trying to find it. And it's kind of believed that basically there's a lot of different forms that all the weights in the network could take, and they'll give you very similar performance on whatever metric you've decided. So in that case, there is no right solution in a single sense, but you just want to find a solution, set of weights that does what you want the network to do in total.
Yeah, so the model might not have like one unique answer that it's supposed to obtain, but you've specified what the spirit of the right answer is when you specify the problem.
Yeah, and in the Netflix example, like, it just is a problem that the human being trying to come up with the, say, recommendation system has to deal with. What do they mean by right? So they just come up with some metric, right? Like, so some metric might be how likely is the person that you recommend the new TV show to, how likely is that person to watch it or something like that.
Or watch it and rate it highly.
Watch it and rate it highly. I don't know what their metrics actually are, but
they pick something that they deem reasonable.
Yeah.
I'm completely with you, and I can see why I wouldn't even call it sweeping under the rug. I see what you're saying. You bring in the human element, and it's no longer the nature of the program, it's the nature of whatever, the experiment or something.
You could have like a really crazily abstract learning goal or something, like the profit of the Netflix company or something, right? Like, if you had like a really big,
a little bit removed and a few extra parameters representing like the CEO's behavior or something like that.
I think that would be worth the effort if you could solve it.
Maybe that's how companies will be run in the future, you know?
Speaking of abstract problems, so I thought of this as a separate problem to the one you're talking about, but maybe they are the same. Deep learning is obviously so often involved with talking about AI and stuff. But AI as a concept, when people think of AI, they don't think of, I'm not saying solving for Netflix is simple, but simpler problems, more complex problems, like, just to be annoying, is this poem beautiful, right? And it seems like there's no way that my question is, can deep learning actually teach us things that we didn't know about the problem?
Well, I mean, if you had an English professor label the data set.
Yeah. If you told the net what is beautiful and what isn't, it'll come up with some set of weights that will spit out a label for a new poem, and maybe that'll tell you something. Maybe you'll learn what's beautiful, or you'll be able to use something about the network to extract some information. I mean, it's only as good as like you believe the network is.
But again, like, there are different things you can do, right? So there's like explicitly supervised learning, where it's like, I'm telling you how beautiful each poem is, and I want you to learn features that will, correctly kind of specify how beautiful a poem is. And
so basically that would be learning the preferences of the person who labeled all the data.
Right.
You can't pretend that you're learning something more general than that. You're learning whatever the labeled data
But what does a real person do when they're trying to be a good poet, right? I mean, suppose, right, I'm a romantic poet. My cost function in writing poems might be something like, what are the kinds of responses that I elicit in other human beings when I read them, my poems? And so that you could build a cost function out of that. It would be something to do with,
like human nature.
It's something to do with human nature, how they're going to react to the poems, and what I'm trying to make them do. I'm trying to make them cry. Am I trying to make them laugh? Am I trying to, whatever, these kinds of more abstract things to do with like other agents and stuff.
So maybe
this could be turned into
and a good way of thinking about this then to like test it might be, hey, if I can build a system which can produce poems which cause the people who listen to those poems to cry, then I've captured something about what sad poetry is.
Yeah, another interesting thing, again, it's kind of a cool example, right, is you can do things that are kind of unsupervised. Like, for example, if you took a large body of poems considered good by, culture or something, you could do kind of various things. Like, for example, you could build networks that would read in a certain amount of a poem, and then the cost function, you would train it to kind of predict some next bit of the poem, for example. And if you built a network that could successfully do that, you might be able to like start it on a word and then have it like automatically kind of produce a poem by feeding in its output.
And so that wouldn't require actually labeling anything about what each individual poem does to someone. It would just be this model that represents basically statistical relationships between words and poems, and
in real poems.
Yeah, what's likely to be the next part of the poem after a given part.
Yeah, and that's obviously a part of what human beings do, right? When a poet learns to be a poet, they read a lot of other poems that are considered good poems, and they probably do learn this kind of statistical structure, you know. So, I mean, I think a lot of, when it comes to more complex artificial intelligence, at least on a really abstract kind of hand-wavy level, it's often quite easy to conceptualize, at least, how fairly complicated intelligence problems can be posed within frameworks that we can already specify.
But it might take a lot of work.
But it might be very difficult to make them actually work. Yeah.
But just the general notion of, you know, it doesn't seem like deep learning can speak to aesthetics or something like that. There are people who are already doing it for exactly that kind of thing, for reading emotions and pictures of faces, or rating things about fashion and all that kind of stuff. So it's all just about if you have the supervised data.
Yeah, and like a thing that people like to do, like that's popular for text processing, is like sentiment analysis of, let's say, tweets, where you have some short, you know, tweet, and you want to say, is it like positive or negative? So that way, like a company, if there's tweets about that company, can just like automatically say, oh yeah, 90% of the tweets about our company are positive. That's good.
It's also very common to do that on movie reviews, because movie reviews are tricky in that people will often write, you know, while this movie was fast-paced and, you know, full of action, ultimately it failed to deliver sentiment or something like that. And then it's kind of confusing because the network sees words like, ooh, fast-paced and like full of action, like those are good words, but should it say that the overall sentiment was bad of that review? So it can be complicated, but there already are networks that are working on this kind of thing.
To me, that's one of the most kind of fun. I mean, I don't work on this stuff per se, but I think about it a bit and talk to people who do it and stuff. It's kind of it's very kind of rewarding. I don't know, when you start realizing that people are having some success, and you start thinking, oh, but more complicated problems are more complicated. A lot of the time, you know, you can at least think of how you could pose them as problems that could be solved with kind of things we already have. And then whether or not they can be is somehow an empirical question. But yeah. Questions, Ryan?
Well, I have 1,700 questions. I'm trying to stay relevant to what you guys are talking about. This thing that you said that I know that a lot of people who aren't part of the field would talk about, of like a machine that learns a poem based on learning from previous poems, and humans think like that. Now, I see the logic in that answer. I get it. It makes sense to me. It's contextually relevant. A lot of people would have just a general problem with that, saying, no, but learning poetry is more about understanding beauty and how it makes you feel and all this kind of thing. And so my question is, when we start to apply our understanding of neural networks, deep learning, and so on, to see how human beings behave, animals behave, and so on, does it look like a lot of the actual, when we find out the answers to these questions, the solutions that we get are going to be simpler than we thought? Is that going to take away a level of complexity that humans feel that they have about themselves?
I think we're kind of far away from that.
Well, it depends on how you look at it, because originally, like the starting of the field of computer vision was someone probably in the 60s, I think, at MIT, putting out this invitation that they were going to have a summer workshop to get computers to do vision. So they thought it was like a 3-month problem, and it turns out it's been many, many decades and it's still not completely solved. So that kind of made us feel like it was actually a far more interesting and complex problem than we thought it was. But then, now that we have these networks that can write captions to images, I think for some reason that has shifted people to feel like, oh, maybe writing isn't so like human as we think it is. You can just do it based on very simple or relatively simple models. So I think it goes both ways, because when you really delve into the problem, you can actually find it to be incredibly complicated. But then once you solve it, it can't be considered complicated anymore because it's solved, I guess.
Humans are pretty, like, we don't make a lot of errors, you know? It's like, I feel like a lot of these, I don't know, I mean, that's true, right? In terms of writing a caption for an image.
Sure.
Like,
yeah,
these are not as good as people like to talk about them.
No, they usually, when you see a talk that shows you some of the results of captioning. They pick out their best ones.
Yeah, but often they pick out their worst ones.
But worst ones in a funny
dishonest,
way.
But the worst ones are like ridiculous. I mean, it's not like it isn't the case that people are making like big strides on difficult problems, and it's really cool.
Yeah, but often
any
failure modes of these kinds of approaches are still like catastrophic failure.
And they seem
like there's a man walking, and it's like it's a submarine.
Yeah, and it seems ridiculous. Like it's like no human being would ever. So there's like we're definitely kind of magical, according to like current understanding. I think that's the case.
Yeah. But I mean, they might get much better.
Yeah, let's assume that they'll get better.
So
yeah, I guess. But I don't think anybody could really claim to have a good, like, empirically well-founded sense of kind of when, computers will be as good as.
But people say this based on. I mean, the futurologists and such like to make
nuts.
Well, they like to make assertions about when the computers will like at least technically be on par with humans.
Well, on I think on MNIST, the digit data set, the computers perform better than humans, but I don't know what that means because that suggests that the person wrote down a number that even that person would not know what they meant when they wrote it down if the computer calls it something different.
Well, they made a slip with their pen, and
Yeah, but compared to human labels, like a person looks at that number.
It has to be the case that if the people were doing it were putting in like full effort, then.
I don't actually know the example you're using.
We spoke about the digits for looking at like zip codes on envelopes, and they wanted an automated process for that. And that data set is used so much to test out algorithms that they compare performance of an algorithm on that data set compared to human labels of that data set. So they'll have like a bunch of people label an image, and then they'll take the most frequent label for that image as like the true answer. And they're claiming that in some ways, algorithms can perform better than humans, but I'm never quite sure what that means. I guess maybe average
because
than a
humans
specific
label
human. Yeah.
And what humans are we talking about? Are we talking about the average human, or are we talking about postman?
Well, it depends.
They should be very good.
Yeah,
they should beat
true.
the computers. That brings up something interesting. So, going into training anyway, and I have a feeling we're going to go there with this. When it comes to errors, right? We're talking about a good program, model is one that will have a low error rating, say on classification. And yet, when they're doing something like writing a caption, suddenly the errors can be wildly inappropriate. Now, with a human, on the other hand, we might be better and make less errors, but more importantly, it seems like the size of our error when we make one is generally smaller as well. Do those go hand in hand? Are they separate properties of the learning? What's that about?
Well, so maybe first let's like just briefly. I mean, I think it's beyond the scope of this to fully talk about training models, but maybe we could just briefly mention that sort of the standard way of training models is something called backpropagation, which basically means that if you have your error function at the top of your network,
which is like how far you are from what's considered the right answer.
Yeah, correct labels.
By
some measure, which is specified by the people who designed the algorithm. Then basically you want to, in a principled way that is fairly straightforward to compute and has been known for decades at this point, you basically can tweak all of the parameters in your model such that they do a little bit better on the data that you've got available for training. And you can just repeat that process. Tweak all of your weights in your model, all of the parameters in your model, so that they're slightly better for the error. They do slightly better with respect to the current objective function on your errors. And you just repeat that. You just keep on tweaking those weights repeatedly.
So technically, you're just moving closer to performing better on the exact images that you trained on, but because
those are representative,
that you can perform well generally beyond those images.
What do we mean by good performance? If I make a mistake, is a huge mistake worth the same as a tiny mistake?
It depends on
the objective function. Depends on how people have defined it.
Yeah, you can make it such that there's some metric that actually corresponds to what humans would consider large or small mistakes. But a lot of times, especially in classification, that's not really what's done. It's just, are you correct or not?
Correct. Yeah. So like, a monkey to a gorilla as your classification mistake would be considered of equal magnitude as a monkey to a school bus. according to some objective functions. According to other objective functions, those could be the monkey to gorilla misclassification, could be a lesser penalized mistake. And so that's a choice in how you design the algorithm. And that kind of gets at the spirit of your question, I think, as well.
It definitely does. I'm thinking about it in terms of how humans behave and then what we're talking about getting out of this learning. I mean, would it be completely incorrect now to jump back a bit in time? We talked about how neural networks and the brain has been evolving. If we go back and back and back until the brain just started to be started the first neurons, the first small biological neural networks up there. Do you think they were similar to what we're working with now? Do you think that biological neural networks went through a similar type of change as to what we're doing in learning?
My intuition is that it wouldn't have been exactly the same because, for a number of things. It's not like the first problem that evolution posed to the nervous systems of proto-animals was to classify handwritten digits, right? Rather it was move like one muscle as a jellyfish so that you can escape from being eaten, or if you're like a worm, to move towards sunlight or something like this.
It's kind of like the original perceptron, if it's like a go, no-go thing.
Yeah,
given these inputs, you think there's something near you, should you spend the energy to flee or not?
You can view that in an abstract way as like a classification task. At any given moment in time, should you make your one possible action or not make your one possible action? And in a sense, that's a classification problem. So maybe there's more similarity than I was initially giving it. But certainly, like, the domain of problem is not the same, right? It's not the case that you have a 500 by 500 pixel image as the first nervous system, and you're trying to like categorize that for objects. The domain was, I suspect, much simpler and had more to do with doing slightly longer term calculations with respect to like muscle movements and things like that.
Like a very completely uneducated point of view of learning and artificial intelligence leads you to think that, hey, maybe what those weird computer guys are trying to do is, build something now that thinks like a baby, and then later it'll think like an adult and it'll be more clever. And then you read anything about it and you're like, no, that's not it. And so my understanding of learning has gone more to a level of, imagine just a small neural network of a few brain cells or whatever it is, perceptrons, and then how that changes over time, how you add perceptrons and it can start to have more functions or whatever. Now I'm starting to get the idea that what we're doing isn't actually like that. We're directing it much, much more than that.
Yeah, usually it's really directed. You start with an architecture and you want to solve one very specific task. What an agent does in the world is like very complicated. And you solve many, many different tasks, each of which is a difficult task by itself that you could use a neural network to do. And we string all of these things together in some kind of real-time way, presumably governed by goals and objectives that exist on kind of multiple scales, both in time and space and stuff like this. There are other agents. The degree to which our learning is supervised is very variable. Like, sometimes it's highly supervised, sometimes completely unsupervised. Sometimes it's kind of through just, seeking rewards, these kinds of things.
So I don't know if we explicitly stated, because most of what we've been talking about has been supervised learning where you have labeled examples.
Yeah, where you're told explicitly
the right
answer.
And unsupervised learning is what we briefly mentioned, where you're not given labels and you're just kind of learning the structure that exists in the inputs that you're given.
Yeah, and then there's kind of reinforcement learning, which is more related to the idea of an agent, which is the idea that you can formulate what an agent, a being in some kind of environment, does as seeking reward. What that agent finds rewarding is somehow part of the specification of the agent. So for humans, it's, we have complicated goals, but some of our simple goals are food. We find food rewarding. We find sex rewarding. We find social interactions of certain kinds rewarding, and other things like that. So there's this other kind of, it's not necessarily separate, but there's this sort of thing people call, reinforcement learning, which is to do with, given an environment that has certain mapping from what an agent does and where the agent is to the reward the agent receives, how should the agent learn to behave?
And kind of the large recent example of this was a paper where they were able to have a deep neural network learn to play Atari games by just being given the pixel values of the screen and, access to controllers.
And the score.
Yeah, and the score.
The
so
score
it knew when it
like
was being
reward.
rewarded. It had to learn all of the structure in the visual input to understand kind of how it could act in the world, and then it had to spit out outputs, which are usually, up, down, left, right, whatever the controllers are.
Yeah.
And they got quite good at it.
Yeah, so this is quite agenty in a way, right? That's pretty similar to the way a human being would learn to play that game. Obviously, for a human being, they have to actually control their whole body to control the 4 buttons that are relevant or something, so that's a separate thing. But theoretically, you see a screen, you get visual input from the screen, you see the score, so you know kind of how well you're doing in some way that you don't fully understand at the beginning, and you have some set of actions that you can take at each moment. And you play it, and you learn what to do in different situations. And so, they were kind of successful in doing that. So this thing of kind of combining reinforcement learning with deep neural networks, that's like a recent cool thing. So that there's various ways in which it kind of, you can, things naturally go in the direction of being more like just learning to do abstract things in the world as opposed to learning to do one really well-specified, that is a well-specified task, but it's not exactly like just classify this as a banana or a monkey or whatever.
You said about the program, there was the claim that it managed to classify numbers better than human beings. So let's, for the sake of example, use the computer playing Atari. Have we gotten to the point anywhere where we're now actually, through unsupervised learning things that would have taken much longer for us to learn? Can we, for instance, write a program that will play Atari, and then watching it play, we're like, that is such a clever tactic to use. I have to use that when I play Atari.
Yeah, so they had a Nature paper about this recently, and they had human-level performance for some expert, game tester or something like this, and the computer program that was built using deep nets did do better than the human in most of the games, the overwhelming majority of the games, and it discovered some new strategies on some of the games. So I've seen a talk where, specifically on Pac-Man, there was a nice little hack for, like, after you eat one of the things that turns the bad guys vulnerable, going near where they respawn and eating a whole bunch of them really quickly. Like the guy, at least the one person who was the game tester, the human game tester for that game, had never thought of that as a strategy.
But it does take exploration. And the games that it didn't do as well on usually had very long-term dependencies and kind of a sense of knowing that you need to go to one room and pick up a key and go back to the other room and unlock the door and that kind of thing. And so it struggled there. But in the basic understanding of what to do in the simpler games, it performed better than a lot of humans.
So you specifically, you compared it to the human, and you said human-level learning, right? And I imagine that at least if we take short clips, I'm guessing that we could play some clips to people, and so long as they didn't know, they'd be like, oh, that person did well. They wouldn't even realize it was a computer playing or something. So
sure. So with respect to Atari, we've passed the Turing test.
Yes. if Atari was existent when Turing was around, we'd already count AI as completed and moved on to the next problem. But speaking of things like Turing test and AI, I think that what the average person's concept, and they vary wildly, of AI is going to be different for people in the field that are working on this. Some people would probably consider just the fact that it learned that, even though we don't assume it has any concept of what it's learned or anything, that doesn't make any sense. For some people, would be intelligence. For other people, it'd be like, that's nothing. You have to be able to walk up to the console and understand what a console is and all this. What would be the minimum you want to see from neural networks and the use of neural networks together? The minimum performance, the minimum tool that you get out of it that you would consider AI, low level?
I mean, I think people already consider this AI, right? But I mean, just it depends on definition. I mean, this is more a semantic point, and right, this kind of agent is never going to walk up to a console and understand what it is because it doesn't have a body and can't walk and has never seen a console before. But if we took a humanoid robot and gave it a really, really complicated neural network as its brain, by some sort of trivial extension of the way people think about how this must work, if the real human brain is a neural network, in fact, and you build a complicated enough, computer algorithm that is simulating a neural network, then probably, philosophy of mind quibbling aside, probably you're going to get something that can, in some sense, by some definitions, understand what it means to walk up to a console, understand what the console is, and play the games well.
Yeah, I think that most people outside of the field kind of get caught up in notions of emotion and consciousness, and we can't have artificial intelligence because these things can't feel or whatever. And to people inside the field, it doesn't. Those things are irrelevant. Why would you? Yeah. I mean, and if you wanted to create a neural network that could kind of predict an emotional response given some inputs, you could train it to do that. It wouldn't feel in the way that people want it to or anything. But it just, as long as it's performing if it's performing a somewhat complicated task at a very high level of performance, I don't know what else to call that if not some kind of intelligence.
I'm completely with you, by the way. I mean, let's gloss over and move past all that other human baggage stuff that they talk about. But even in just talking about the learning and the tasks and the aptitudes for those tasks, it seems to me that we're consistently talking about one task at a time and one goal. Would a suitably powerful learning module not be suited for multiple tasks to be able to slowly learn to play the Atari and also make an omelette after watching someone do it, that kind of thing? Do they have to be so small as to be one task and you build them up? Or can you have one large neural network and achieve multiple goals?
That was certainly a goal of the field to do that, some sort of general intelligence. Right now, I guess it's pretty specialized.
Yeah, I mean, I think the Atari paper, the kind of a claim they make, which I think is, they don't make it as a super strong claim, but there's a sense in which it's the same computer game playing all the different games, but it's been trained separately on each of the games, right? So that's not exactly the same thing you're asking for.
Is it the same architecture?
It's the same architecture, but the same... the language here differs by country of origin and stuff. This was a paper put out by a research institute, a research group affiliated with Google DeepMind in London, and they say it's the same algorithm for the same agent. I don't remember the exact language, but I think by the parlance that I'd be familiar with, we wouldn't call that the exact same. It would be it would be the same architecture, maybe, or something like this. I mean, this is a quibbling point, so we don't really need to harp on this. But
because you could put all four of those things inside a box that was the head of the thing, and then you could have another little trivial neural network that would recognize which game you're playing or something, and then it activates the right one, right? So yeah.
So the big point, right, is that ideally you want to have something that can do all of this general stuff, but we haven't yet been able to build a setting where you actually need to solve multiple goals and you can't phrase it as one goal. So yes, if we build a humanoid robot, we'll probably want them to have subroutines or something that allows them to switch between different kinds of contexts in which they're performing different kinds of tasks. For the time being, we're not there yet.
So I think we should probably wrap up.
Thank you for talking to us. That was awesome.
Yeah.
Thank you for having me. It was a lot of fun.